Welcome to the Sleepy Scholar. It's lovely to have you here tonight. Wherever you are, whatever the hour, I'm glad you found your way to this quiet corner of the night. Maybe you're tucked under a heavy blanket, with the lamp still glowing in the corner. Maybe you're on a couch with the cushions pressed just right, or on a long train ride watching the dark slide by the window, or lying flat on your back in a room where the only light is the soft one coming from your screen.
Wherever you are, settle in, get comfortable. There's nothing you need to do for the next while except breathe slowly and let your shoulders come down from wherever they've been holding all day. And before we drift off into tonight's subject, let me ask you the question I always like to ask. Where in the world are you watching from tonight? I genuinely love knowing. Some of you are listening at midnight, some at 3 in the morning, when the house has gone completely still, some in the grey hush of an early afternoon nap. If you feel like it, you can tell me down in the comments where you are and what time it is in your corner of the night. It's a small thing, but it makes this feel less like a recording and more like the two of us sitting quietly together in the dark. And if you enjoy these slow journeys, if you'd like more nights like this one, a gentle like and a subscribe really does help this sleepy little channel keep going. I'm a small creator, and honestly, that kind of support means more than I can say. It's the thing that lets me keep making these.
And to those of you who are already subscribed, who come back night after night to drift off with me, thank you. Truly, you're the reason the lamp stays on. Now, tonight, I want to tell you something a little strange, something that once you hear it, you may never quite shake. And I'll warn you the way I always do, I'll try not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something. A fair trade, I think.
Here it is. Every single image you have ever seen of the center of our galaxy is, in a quiet way, a lie. Not a malicious one. Not a trick. But a lie your eyes were never meant to see because your eyes could never have seen it at all. Not one of those pictures. Not the swirling golden clouds, not the glowing ring, not the dense, glittering crowd of stars at the heart of everything. Not one of them is made of the kind of light your eyes are built to catch. You have never seen the center of the galaxy as it actually is. And here's the part that's hard to let go of once you've heard it. You never will. Not from where you're lying right now. Not from the surface of this planet. It's simply not possible. The light that would let you see it never arrives. It dies on the way.
I know, stay with me. We'll take this slowly the way we take everything here. One soft idea at a time, like stepping stones across a dark pond. There's no rush at all. If you drift off somewhere in the middle of this, that's perfectly fine. The galaxy will still be turning when you wake, and the ideas will still be here waiting for you. You don't have to hold on to every word. You don't have to understand every piece. You just have to let the sound of it carry you somewhere gentle.
So let me explain what I mean, because I don't want to leave you with just a riddle and no comfort. When you picture the center of our galaxy, the Milky Way, the great wheel of stars we live inside, you probably imagine something bright, a blazing core, a dense knot of light somewhere far off in the dark. And you'd be right that something extraordinary is there. There is a center, there is a heart to all of this. But between you and that heart lies a problem, a vast, soft, drifting problem. Dust. Not the kind of dust that gathers on a windowsill or floats in a sunbeam in your living room, though it's a little like that. This is interstellar dust, enormous clouds of it, tiny grains of carbon and silicate and ice scattered through the long, flat plane of the galaxy. Think of the galaxy as a great spinning dinner plate of stars, and we live out on the rim of it, a little more than halfway out from the middle. To look toward the center, we have to look straight along the flat of the plate. And along that flat, edge-on, is exactly where all that dust piles up the thickest. We're trying to see the brightest room in the house, but we're looking at it through wall after wall after wall of smoke. Now here's where I want you to really feel the scale of it, because the number is almost unbelievable, and it's the heart of why I said you've never truly seen the center. Astronomers measure how much light gets blocked using something called magnitudes of extinction. You don't need to remember the word, just hold on to the picture. Extinction is simply how much the dust dims the light coming through it toward the center of the galaxy in the kind of visible light your eyes use. The ordinary light of a candle, a street lamp, a star you can see with the naked eye. The extinction is more than 30 magnitudes. More than 30. And that scale, the magnitude scale, it isn't gentle. It isn't like turning a dimmer switch down a third of the way. Each step is a multiplying step. By the time you stack up 30 of them, you arrive at a number that's hard to even hold in your mind. Of every single photon of visible light, every tiny particle of ordinary light that sets out from the galactic center heading toward your eye, fewer than 1 in a trillion survives the trip. Let me say that again, slowly, because it deserves to be said slowly. 1 in a trillion. For every trillion little packets of visible light that leave the heart of the galaxy and start the long journey toward Earth, all but 1 of them is swallowed by the dust along the way, absorbed, scattered, lost, gone. Imagine a trillion people setting out on a long walk, and only 1 of them ever reaching the other side. Imagine pouring out a trillion grains of sand and finding at the end that just a single grain made it through. That's how much of the center's true visible light reaches us. Effectively none, effectively nothing. The core is invisible to optical telescopes, not faint, not blurry, invisible, as good as not there at all as far as ordinary light is concerned. So when you've looked at a photo of the galactic center and thought, there it is, there's the middle of the galaxy, what you were actually looking at was a translation. A picture made from light your eyes can't perceive at all, gathered by machines that can sense what we cannot, and then painted by human hands and computers into colors you can see. Every golden glow, every fiery orange swirl, those colors were chosen for you. They're a kindness.
A way of making the unseeable visible to a creature like you, who simply was not built to look at this thing. And isn't that a strange and tender idea to sit with? That there's a place at the very heart of the home we live in, the galaxy that holds every star you've ever wished on, and you cannot see it. You will never see it with your own 2 eyes. No human ever has. No human ever will. Not in visible light. Not from here.
It's hidden gently and completely behind a veil of drifting dust as old as the galaxy itself. But I told you there were 2 illusions tonight. 2 reasons you've never seen the center as it actually is. The dust is only the first. The second is, if anything, stranger still, and I think it's the one that will follow you into your dreams. Even the light we do manage to collect, and we do manage to collect some, I promise, and I'll tell you exactly how, even that light is old. Not a little old. Astonishingly, achingly old. The center of our galaxy is about 26,000 light-years away, and a light-year, remember, is a measure of distance, not time. It's how far light travels in a single year, and light is the fastest thing there is, the absolute speed limit of the universe. Nothing outruns it. So when we say the center is 26,000 light-years away, we're saying that light, moving at the fastest pace anything can ever move, takes 26,000 years to cross the gap between there and here. Now follow that thread with me slowly, because here's where it gets quietly astonishing. The light arriving from the galaxy's heart tonight, the light that astronomers are catching right now in their great machines, that light did not leave recently. It set out 26,000 years ago, it has been traveling alone through the cold and the dark since long before there were cities, before there was writing, before there was anything we'd recognize as the modern world. It left when your ancestors were still living in caves, when they were still pressing their handprints onto stone walls by firelight. 26,000 years ago. Let that number settle over you like a blanket. The famous cave paintings at Lascaux, those beautiful ochre horses and bulls galloping across the rock, those are about 17,000 years old, younger than this light. The even older paintings at Chauvet, the lions and rhinos drawn in charcoal in the deep dark of a French cave, those are about 36,000 years old, older than this light. So the light reaching us from the galactic center tonight left somewhere in that long, dim window when human beings, our own kind, with hands like yours, were crouched in the flickering glow of a fire, dragging colored earth across stone to draw the animals they hunted and feared and loved. That's the snapshot we receive. That's the only version of the center we will ever have. It's a picture from the deep past, a postcard mailed across an unimaginable distance, written in the upper Paleolithic, only just now sliding through the slot. And here is the thought that I find genuinely hard to put down, the one I want you to carry softly into sleep. Whatever is actually happening at the center of the galaxy right now, at this very moment as you lie here breathing, we have no way of knowing. None. It's not that we haven't looked hard enough or built good enough instruments. It's that the information physically cannot reach us. The light that could tell us hasn't been made yet, or rather it has. But it's only 26,000 years into a 26,000-year journey. It only just began. It won't arrive for another 26,000 years. No one alive today, no one in any nation, no scientist with any telescope will ever know what the heart of our galaxy looks like tonight. That knowledge is sealed away by the simple, unbreakable speed of light. It belongs to people who haven't been born yet in a world we can't imagine. 26,000 years from now.
They'll see tonight. We never will. So you see what I mean? You have never seen the center of the galaxy as it actually is. Not in the light your eyes use because the dust devours it, and not in the present because every glimpse we get is a fossil of deep time. A double illusion. A thing hidden twice over. And yet, and this is the part that makes the whole thing beautiful rather than sad, we know it. We know it astonishingly well. Better than ever before.
We know what's there and how heavy it is and how far away it sits, to a precision that would have seemed like sorcery just a generation ago. We have come to know the unseeable, and the story of how we did that, the story I want to tell you over these slow hours, is one of the most quietly heroic things our species has ever done. But not yet. We're going slowly tonight, remember. No rush. There's all the time in the world, and most of it is dark and quiet and made for resting. Let me give you something to hold while you drift, a way to actually picture the dust I've been talking about, because it's not some abstract thing locked away in a textbook. You can see it. You've probably seen it already on some clear night, far from the lights of a city, and never known what you were looking at. If you've ever been somewhere truly dark and out in the countryside, up a mountain in a desert where the night comes down hard and complete and the stars don't just dot the sky but flood it, then you may have seen the Milky Way itself. Not a single star, but the whole great band of it, a soft river of pale light arching all the way across the sky from one horizon to the other. That milky glow is the combined light of countless distant stars, all the stars of our galaxy's flat plane, blurred together by sheer distance into a luminous mist. It's our own galaxy, seen from the inside, edge on, the way you'd see the rim of a plate if you held it up to your eye. And in the summer sky, if you trace that band of light down toward the horizon, down toward the constellation of Sagittarius, that's where the Milky Way grows brightest and thickest and most crowded. That's where you're looking toward the center. That bright bulge low in the summer sky is the direction of the galactic heart. So in a way, you have looked right at it. You've turned your face toward the center of the galaxy, and your eyes have taken in that soft glow. But look closer at that bright band and you'll notice something. Right through the middle of the glowing river, splitting it, there are dark lanes, channels of blackness, like cracks in the light, like ink poured into the milk. The old sky watchers called this the Great Rift. It looks on a clear dark night like a great dark gash dividing the summer Milky Way down its length. For a long time, people imagined those dark patches were empty, gaps in the stars, windows onto the nothing beyond. But they're not empty. Not at all. Those dark lanes are the very opposite of empty. They are the dust. Those black channels splitting the bright summer Milky Way are enormous clouds of interstellar dust hanging between us and the stars behind them, blocking out the light. The Great Rift isn't a hole in the galaxy. It's a curtain. And it's exactly the curtain, the same dust, the same drifting clouds, that hides the center from us. So the next time you're under a dark sky in summer and you find that bright bulge in Sagittarius and you see the dark rifts cutting through it, you can know what you're really seeing. You're looking straight at the direction of the galactic center, and the darkness lying across it, the very thing blocking your view, is the answer to why you can't see what's behind it. You are, in that moment, looking directly at the reason you cannot look. The veil and the thing it hides, both in the same patch of sky. There's something almost poetic in that, isn't there? The barrier announcing itself, sitting right there in the open, dark and quiet, daring you to see through it. And you can't. Your eyes simply can't. The dust wins, 1 trillion to 1. So here's the question I want to leave hanging in the dark between us, the puzzle we'll spend the night gently untangling. If the center is hidden behind a veil of dust so thick that fewer than 1 photon of visible light in a trillion ever makes it through, if your eyes and ordinary telescopes and cameras built for ordinary light are all completely blind to it, then how on earth do we have any image of it at all? How do we have those golden, swirling pictures? How did we ever take the measure of a thing we cannot see? How can anyone claim to know what sits at the heart of the galaxy if the heart of the galaxy is invisible? There is an answer. There's a beautiful, clever, patient answer, and it involves light your eyes were never designed to perceive, light that slips through the dust like water through a sieve. It involves a single, lonely star racing through the dark at a speed I can hardly believe even as I say it, and a handful of human beings who watched that star faithfully for decades, and in watching it, weighed the unseeable monster it was circling. It involves a Nobel Prize and Albert Einstein being proven right in the strangest place imaginable, and a photograph that isn't really a photograph at all. But all of that is for the hours ahead. For now, just hold the mystery gently. The center is there. We can't see it. And yet somehow we know it. Let that sit with you, soft and strange, like a question you don't need to answer before morning. Take a slow breath if you'd like. Let it out slowly. You're doing nothing wrong by drifting. There's nowhere you need to be but here, in the quiet, looking up at a heart you cannot see, 26,000 years away, where the light left when someone very much like you was pressing a hand to cold stone and leaving a mark that said simply, I was here. We'll keep going in just a moment. Slowly. Always slowly. There's no rush at all. Let me sit with you a little longer in this idea of the dust, because I don't want to leave it as just a number, just a fact to swallow and move past. I want you to feel what it actually means, this veil between us and the center, because it changes the whole way you might think about looking up at all. You know how, on a foggy night, a street lamp 2 blocks away seems to vanish completely, while the one right above you still glows? The fog doesn't stop all the light at once. It eats it gradually, a little more with every meter the light has to travel through it. The farther away the lamp, the more fog the light must cross, the dimmer it gets, until somewhere out there is a lamp that's still burning brightly, but that you simply cannot see, because every last bit of its light was absorbed before it reached you. It's not off, it's not broken, it's just lost behind the fog. Now stretch that picture out across an unthinkable distance. The center of the galaxy is a blazing, crowded, brilliant place. Millions upon millions of stars packed close together, far more light pouring out of that one region than from anywhere else in the galaxy. If the dust weren't there, the galactic center would be a glory in our night sky. It would be a great bright glow, far brighter than anything else up there. A permanent soft beacon riding low in the summer dark. People would have built temples facing it. It would be in every poem ever written about the night. But the fog is there, the dust is there, and it's not 2 blocks of fog, and it's 26,000 light years of it, on and off, clump after clump, cloud after cloud, all the way in. And so that great central glory, that blazing heart that ought to dominate our sky, is dimmed not by half, not by 99%, but by a factor of more than 1 trillion. Snuffed out for our eyes as if someone had drawn a heavy curtain across the brightest window in the universe and told us, gently, that this part of the house was not for us to see. And I find there's something oddly comforting in that, rather than something to mourn. The galaxy keeps its heart private. It holds its deepest center close, wrapped in soft, dark clouds, the way you might cup your hands around a candle flame to keep it from the wind. The brightest thing is also the most hidden thing. The most crowded place is the one that looks to our naked eyes like emptiness, like that dark rift splitting the summer sky. There's a kind of modesty to it. The galaxy doesn't show off its center. You have to earn the sight of it with patience and cleverness and instruments that see beyond the reach of human eyes. And here's one more gentle thing to turn over as you lie there. That dust, the very stuff blocking our view. It isn't an enemy, not really, even though it stands between us and the thing we most want to see. That dust is the raw material of new stars. It's the stuff that clouds collapse out of, the stuff that gathers and warms and ignites into the next generation of suns, the next generation of planets, perhaps even somewhere, the next generation of someone lying awake at night wondering about all of this. The same dust that hides the center is the dust that makes new worlds. The curtain is also the cradle. So when you picture that veil now, maybe don't picture only a barrier. Picture a vast, soft, dark nursery drifting between you and the heart of everything, slowly, over millions of years, gathering itself into new points of light. The center is hidden behind the place where new stars are born. There are worse things to have standing in your way. Breathe slowly. You're doing beautifully, just lying there, just listening. The dark is kind tonight, and we have a long way still to drift, because the question still hangs there, doesn't it, soft and unanswered in the quiet between us. If the dust is that thick, if visible light dies 1 trillion to 1 trying to cross it, then how do we have any picture of the center at all? How did we ever come to know the thing behind the curtain? The answer begins with a simple, almost surprising idea. not all light is the same. The light your eyes can see, red and orange and yellow and green and blue and violet, the colors of a rainbow, the colors of the world, that's only a tiny, narrow slice of a much, much wider range of light that exists out there in the universe. There's light beyond red, light too red for your eyes to catch that we call infrared, and light beyond that still far longer and gentler waves that we call radio, and light shorter than violet, more energetic, that runs out into the ultraviolet and the X-rays and beyond. Your eyes were tuned over millions of years of evolution to just one small band in the middle of all that. The band that the sun shines most brightly in, the band that passes easily through Earth's air and water. You see the slice that was useful for a creature living on the surface of this particular planet. No more, no less. But the universe doesn't care what your eyes were tuned for. It sends out all of it, the whole vast range, and the different kinds of light behave in wonderfully different ways when they meet that wall of interstellar dust. And that difference, with that simple fact that infrared and radio waves can do something visible light cannot, that is the key that finally unlocks the hidden center. That's the door in the curtain. But how that door works, and the lonely racing star that walked us through it, and the patient watchers who followed it for decades through the dark, that's where we'll go next, slowly, when you've settled a little deeper into the quiet. For now, just rest with what you've gathered tonight. The center is real. It's hidden twice over. Once by dust, once by time. You've never seen it, and you never will, not with these eyes, not from here. And somehow, beautifully, impossibly, we know it anyway. We've learned to see in light we were never given. We've learned to read a postcard written 26,000 years ago by the simple fact that it finally arrived. There's no rush to understand all of it. The ideas will keep. The galaxy will keep turning whether you follow every word or let yourself slip away mid-thought. That's allowed. That's what this is for. So let your eyes go heavy if they want to. Let the dark room hold you. Somewhere out there, low in the summer sky, behind a veil of dust as old as the stars, the heart of our galaxy is glowing, unseen, sending its ancient light across an ocean of years toward a planet where someone lies quietly, listening, finally beginning to understand just how strange and lovely it is to look up at a thing you cannot see. And we've only just begun to lift the veil. Welcome to the Sleepy Scholar. It's lovely to have you here tonight, wherever you happen to be. Maybe you're tucked under a heavy blanket with the lamp still glowing softly in the corner. Maybe you're on a long train, watching the dark slide past the window. Maybe it's the middle of the night and the house has finally gone quiet around you. Wherever you are, settle in. You don't have to do anything but breathe and let the words wash over you. And before we drift any deeper, just a small thing. If you enjoy these slow journeys through big, strange, beautiful ideas, a gentle like and subscribe really does help this sleepy little channel keep going. Small creators like me rely on your kindness more than you'd guess, and it means the world. And to those of you already here, already part of this quiet ritual, thank you. Truly. So tell me, before you fade away, where in the world are you watching from tonight? What time is it in your corner of the dark? I always love to imagine all of you out there, scattered across the night, listening together. Now, let me tell you something strange, and I'll try not to make it so interesting it keeps you awake. Though if it does, well, at least you'll have learned something. A fair trade, I think. Here it is. Every single image you have ever seen of the center of our galaxy is, in a quiet way, a lie. Not a deception, not a trick anyone meant to play on you. but a lie all the same, because none of those pictures show you what your eyes were ever built to see. Not one of them is visible light. You have never seen the heart of the Milky Way as it actually is. And the strangest part? You never will. Not with these eyes, not from where you're lying right now. There are two reasons for that, and both of them are gentle, and both of them are astonishing, and we'll take them one at a time, slowly, with no hurry at all. The first reason is dust. Out there, lying flat along the plane of our galaxy, between us and the center, there is an ocean of fine interstellar dust. Not the kind that gathers on your bookshelf. Something far thinner, far colder, scattered across thousands of light years of space, and yet there's so much of it, packed so deep along that line of sight, that it does something almost unbelievable to visible light. The dimming, the extinction as astronomers call it, runs to more than 30 magnitudes. I know that number means nothing on its own, so let me translate it into something you can hold. It means that for every trillion photons of visible light that's set out from the center toward us, fewer than one survives the crossing. 1 in a trillion. The rest are absorbed, scattered, swallowed by the dust long before they ever reach the sky above your roof. The center, in the light your eyes use, is for all purposes simply invisible. A black curtain drawn across the brightest, busiest place in our galaxy. So that's the first veil, dust. But there's a second veil, and this one is even stranger because it isn't made of anything at all. It's made of time. Light is fast, faster than anything, but it isn't infinitely fast. It takes its time crossing the great distances of space, and the center of our galaxy is far, about 26,000 light-years away, a distance now measured so precisely that we know it to better than a fraction of a percent. Which means the light arriving from the galaxy's heart tonight, the faint glow we collect with our instruments, did not leave there recently. It left 26,000 years ago. Let that settle for a moment. 26,000 years. When that light began its long journey toward you, there were no cities, no writing, no farms. Our ancestors were still hunters, wrapped in fur, moving across a colder world. And in the dark of certain caves, by the flicker of small fires, some of them were pressing their hands to stone walls and painting. The horses and bulls of Lascaux are around 17,000 years old. The lions and rhinos of Chauvet, older still, some 36,000 years. So somewhere right in that long window, while human beings were first learning to leave images of the world on cave walls, the light you might glimpse tonight was just setting out across the void, which leads to a quiet, almost dizzying thought. Whatever is truly happening at the center of our galaxy at this very moment, right now, as you lie there breathing, no one alive will ever know. Not you, not me, not anyone. The news of it won't arrive for another 26,000 years. We are not watching the center. We are reading a postcard written in a hand we can't quite see that has only just now reached our door after the longest journey imaginable. So the center is hidden twice over, once behind dust, once behind time, and you don't have to hold both of those at once. You can let one slip away and keep the other, or let them both go soft at the edges. There's no test at the end of this. The whole point is to rest. Here, let me give you something you can actually see the next time you find yourself under a truly dark sky in summer. Look toward the constellation Sagittarius, low along the horizon, where the Milky Way swells brightest and thickest, a great glowing river of distant stars. That bright bulge is the direction of the center, but run your eye along it and you'll notice the band is split, torn down the middle by long dark lanes where the light seems to simply stop. Astronomers call that the Great Rift. And here is the gentle secret of it. Those dark lanes are not empty. They are not holes in the galaxy. They are the very dust we've been speaking of, the same dust that swallows the center's visible light by that factor of 1 trillion. When you look toward the heart of the Milky Way, the heart itself is hidden right there, just behind those dark, dust-laden rivers. You are looking straight at the curtain and mistaking it for the stage. So a question must be forming somewhere in the drowsy back of your mind. If visible light never makes it through, if the center is buried under 30 magnitudes of dust and 26,000 years of distance, then how on earth do we have any image of it at all? How do we have anything to show? And that question, how do we have any image at all, is exactly where we're going next. The answer begins with something your eye does every autumn evening without you noticing. When the sun goes down and the sky deepens from orange to violet to black, the first stars you see are the brightest ones, and you see them easily, effortlessly, without any instrument at all. But if I asked you to look through a handful of fog, or through a thin curtain, or through the colored glass of a bottle, you'd see something maybe, but the shapes would be blurred, the colors changed, the brightness dimmed. What you see depends entirely on the kind of light you're using, and on what the light has to travel through. Visible light, the red and orange and yellow and green and blue that your eyes are tuned to, behaves rather badly when it meets a cloud of dust. It scatters, it gets absorbed, it bounces off the small grains of carbon and silicate and ice that drift through the space between stars, and it never comes out the other side. The longer the path through the dust, the worse the attenuation. And the path from the galactic center to Earth runs right through thousands of light years of the galaxy's thickest, dustiest lanes. By the time a photon of visible light has made that journey, it has almost certainly been swallowed. The number astronomers use for this is roughly 30 magnitudes of extinction in what they call the V-band, the V standing for visible, the band where your eyes naturally see. Now, 30 magnitudes might not mean much on its own, so let me give it to you in a form that lands a little differently. Every 5 magnitudes of extinction cuts the brightness of a source by a factor of 100. That's the rule astronomers use, a logarithmic scale going back to the ancient Greeks, who sorted stars into brightness classes without realizing they'd stumbled onto a mathematical pattern. 5 magnitudes, factor of 100, 10 magnitude, factor of 10,000. 15 magnitudes, a factor of 1 million. 20 magnitudes, 100 million. 25 magnitudes, 10 billion. And 30 magnitudes, the number the galactic center sits behind in visible light, means a dimming factor of around 1 trillion. 1 trillion. If you had 1 trillion grains of sand and you laid them side by side, they would stretch roughly the width of a continent. That is how many visible photons are lost for every single one that would, in some theoretical frictionless universe, make it through the dust from the galactic center to your eye. 1 in 1 trillion makes it. The other 999,999,999,999 are gone, absorbed, scattered, lost to the interstellar dark. So when astronomers point an optical telescope, a visible light telescope, the kind most people picture when they hear the word, toward Sagittarius and toward the galactic center, they see nothing. Not a dim blur, not a faint smudge, nothing. The center doesn't exist in visible light, as far as any telescope on Earth or in orbit is concerned. It is perfectly, absolutely hidden. But here's what saves us. Light is not one thing. It is a family of things, a whole spectrum of wavelengths stretching from the very short and very energetic gamma rays and X-rays through the ultraviolet, through the thin sliver of visible light our eyes respond to, and then out the other side into infrared and radio waves, where the wavelengths grow longer and longer, slower and gentler, less easily scattered. And the key insight, the one that opened the galactic center to human eyes for the first time, is that dust doesn't treat all wavelengths the same way. Visible light, with its shorter wavelengths, interacts readily with the dust grains because the grains are roughly the right size to scatter those particular wavelengths. But longer wavelength infrared light slips past. The dust grains are simply too small and too sparse to catch it with anything like the same efficiency. And radio waves, with their enormously long wavelengths, millimeters, centimeters, meters, practically ignore the dust entirely, the way a deep bass note passes through walls that would reflect a high-pitched whistle. The numbers make this concrete. In the near-infrared, the wavelengths just beyond what your eye can see, the domain of warmth and gentle heat, extinction toward the galactic center drops to roughly 2 to 3 magnitudes, 2 to 3 versus 30 in the optical. That is not a small difference, it is an almost incomprehensible one. Where visible light is dimmed by a factor of 1 trillion, near-infrared light is dimmed by a factor of perhaps 6 to 16. Still a significant loss, but one a sensitive telescope can account for, one that leaves something behind to actually measure. And this is where 2 telescopes perched on 2 different mountaintops on opposite sides of the Pacific Ocean changed everything. The Keck Observatory sits on the summit of Mauna Kea, a dormant volcano on the Big Island of Hawaii, at an altitude of about 4,200 meters, high above most of the water vapor that normally blurs astronomical observations. On a clear night up there, the sky is a different thing altogether. Dark in a way most people never experience, with the stars not twinkling, but burning steady, their light arriving clean through the thin, still air. Keck is home to 2 of the largest optical and infrared telescopes ever built, with primary mirrors 10 meters across, mosaics of hexagonal segments arranged like honeycomb tiles. On the other side of the world, in the high Atacama Desert of northern Chile, sits the Very Large Telescope, the VLT, operated by the European Southern Observatory, which astronomers abbreviate simply as ESO. The VLT is 4 separate telescopes, each with an 8-meter mirror arranged on the plateau of Cerro Paranal at 2,635 meters above sea level in one of the driest places on Earth. The Atacama is so dry that the humidity sometimes approaches 0, and the sky above it is dark and transparent in ways that feel almost unreal. The 4 VLT telescopes can operate independently, or they can be combined into a single virtual instrument, an interferometer, that links their light into one coherent whole, mimicking a telescope with a mirror much larger than any single structure could achieve. Both Keck and the VLT were pointed toward the galactic center, and both of them critically were looking not in visible light, but in the near-infrared, specifically in what astronomers call the K-band, centered on a wavelength of roughly 2.2 microns. To put that in perspective, the human eye is sensitive to wavelengths between roughly 0.38 and 0.70 microns. The K-band sits at 2.2, more than 3 times longer than the reddest light you can see. It is utterly invisible to you, but to an infrared detector, cooled to keep its own heat from drowning out the signal, it opens a window straight through the dust and into the heart of the galaxy. What they saw, decade after decade of careful observation, was a crowded, busy, extraordinary place. Stars moving. Not slowly, the way stars appear to drift across centuries of human timekeeping, but visibly, measurably, moving from year to year, even from month to month. A whole population of stars gathered around a central point, circling something they could not see, something dark and massive and impossibly dense at the very middle of it all. And one star in particular stood apart from the rest. But before we get to that star, and we will very soon because it is really the heart of the whole story, Let me give you the radio side of things, because the dust problem has a second solution, one that came earlier, one that revealed the monster at the center before anyone had the tools to track individual stars. Radio waves, as I said, pass through the interstellar dust the way a deep sound passes through a wall. The dust that blocks visible light completely, the 30 magnitudes, the factor of 1,000,000,000,000, is essentially transparent to radio. A radio telescope doesn't care about the dust at all. It points at the galactic center and receives a signal as if the dust weren't there, as if the path were clear. In 1974, 2 radio astronomers at the National Radio Astronomy Observatory were working with a new instrument, mapping radio emissions across the sky in careful detail. Their names were Bruce Balick and Robert Brown, and on a winter's day, in their data from a region of sky in the direction of Sagittarius, they found something unexpected: a compact, bright, peculiar radio source. Unlike the diffuse emissions that scattered across the galactic center region generally, sitting right at the dynamical heart of the galaxy. Pinpoint, intense, anomalous. They called it Sagittarius A star, written with a symbol Sgr A. The asterisk, the star symbol, Sgr was Robert Brown's invention, added because the source was, in his word, exciting. An excited atom in physics is written with an asterisk, a superscript star, to show it's in an elevated energy state, and this source, whatever it was, deserved that notation. It was not quiet, it was not ordinary, it was something special, sitting right at the center of everything. Now, in 1974, no one was certain what Sgr A was. They knew it was compact and radio bright. They suspected it was something massive and unusual. Over the following years and decades, as radio mapping improved and as other wavelengths were brought to bear, X-ray satellites, infrared observatories, eventually the exquisite near-infrared imaging from Keck and VLT, the picture slowly sharpened into what we now know with great precision. Sagittarius A star is a supermassive black hole. Not a theory, not a best guess, not probably a black hole. A confirmed, measured, Nobel Prize certified supermassive black hole at the gravitational center of the Milky Way galaxy, the anchor point around which everything, including you, including the sun, including every star you've ever seen on a clear night, very slowly orbits. Its mass, as measured by the gravity collaboration working with the VLT interferometer and published in 2019, is approximately 4.154 million solar masses, 4,154,000 times the mass of our own Sun. That number comes from years of precise stellar tracking, from watching stars orbit the invisible center and applying the same physics that lets us know how heavy the Earth is by timing the Moon, or how heavy the Sun is by timing the Earth. Gravity, orbit, geometry. The invisible made legible through motion. 4 million solar masses. Let that settle for a moment. If you could gather 4 million copies of our Sun, each one a blazing sphere of fusing hydrogen, each one 4 million kilometers in diameter, each one producing more energy every second than all of human civilization has ever produced or ever will. And if you somehow compressed all of them together into a single object, you would have something with the mass of Sagittarius A. Not its volume, not its size, just its mass packed down to something unimaginably dense. And here is the contrast that I think captures the strangeness of it better than any other single number. The event horizon of Sgr AC, the boundary sphere around a black hole beyond which nothing, not light, not information, not any physical thing, can escape, has a radius of about 12 million kilometers. That's the Schwarzschild radius, named for Carl Schwarzschild, who derived the mathematics of black holes from Einstein's equations in 1916, the year after general relativity was published, from a trench on the Eastern Front during the First World War. 12 million kilometers in radius. That sounds large, but compare it to the solar system. Mercury, the innermost planet, orbits the Sun at an average distance of about 58 million kilometers. The event horizon of Sagittarius A, the physical boundary of the black hole, the edge of the thing itself, is at 12 million kilometers. It would fit inside Mercury's orbit. You could slide the entire black hole, event horizon and all, into the space between the Sun and its closest planet, with room to spare. Comfortably, with tens of millions of kilometers to breathe. In terms of actual physical size, the Schwarzschild radius corresponds to a diameter of about 24 million kilometers, roughly 17 times the Sun's own diameter, 17 solar diameters. That is a large number when you think about it in human terms, but in astronomical terms, for something containing 4 million solar masses, it is extraordinary smallness. It is the density that matters here, the sheer improbability of packing that much matter into that small a volume. Our Sun is already dense by everyday standards, a ball of hot plasma 1 million kilometers across. Imagine making something 4 million times heavier but only 17 times wider. The numbers don't quite fit the intuition, and that's fine. They don't have to. Let them wash over you. Now, there is one more number I want to give you before we move on to the single star that made all of this certain rather than probable. The distance. This matters more than it might seem at first, because knowing the mass of Sgr A precisely, knowing the distance precisely, pinning down where exactly this thing sits in space, that is what separated a compelling hypothesis from a definitive scientific result. And for most of the 20th century, the distance was not known well. Estimates varied considerably. The number that appeared in astronomy textbooks carried uncertainties of perhaps 10%. And in astronomy, a 10% uncertainty in a distance measurement propagates through everything else you'd like to calculate. The mass, the luminosity, the orbital dynamics. It's like trying to build a house with a ruler that might be off by a foot. The distance to the galactic center is now known to better than 0.3%. That is a number worth sitting with, from 10% uncertainty down to 0.3%. That is not a small improvement. It is a factor of 30, a transformation from imprecision into something approaching certainty. And it was achieved by a collaboration of astronomers working under the umbrella name Gravity, the Gravity Collaboration, using the Very Large Telescope Interferometer in Chile, combining the light from multiple VLT telescopes into an instrument of breathtaking sensitivity and precision. Their 2019 measurement placed the distance to Sagittarius A at 8,078 parsecs. A parsec is a unit of astronomical distance equal to about 3.226 light-years. It's defined by the geometry of parallax measurements, the same principle that makes your finger seem to jump position when you alternate closing one eye, then the other. Multiply 8,378 parsecs by 3.226 and you get approximately 26,673 light-years. The collaboration also published an earlier value in 2018 of 8,127 parsecs. The numbers shifted slightly as the data improved. Both cite comfortably within what is now conventionally quoted as the distance to the galactic center, approximately 26,000 light-years, or about 8 kiloparsecs. 26,000 light-years. A light-year is the distance light travels in 1 year, moving at just under 300,000 kilometers per second. In a single second, light crosses a distance of nearly 300,000 kilometers, about 7.5 times the circumference of the Earth. In a year, it covers roughly 9.46 trillion kilometers. And in 26,000 years, it covers a distance that makes every scale of human experience feel like a single step on a journey measured in continents. The light reaching your eyes from the galactic center tonight, or rather, the infrared and radio signals that our instruments translate for us, since your eyes can't see the center at all. That light, or those waves, left their source when the human world was a profoundly different place. Not historically different, not civilizationally different. Biologically the same as today, yes, the same Homo sapiens who look up at the same stars. But living in a world without cities, without writing, without agriculture, without metalworking, without anything that would be recognizable to you as part of the world you know. The Chauvet cave in southern France contains some of the oldest known cave paintings, dated to around 36,000 years ago. Horses, mammoths, rhinoceroses, a panel of lions rendered in charcoal with a skill and an intention that feels startling when you encounter it for the first time. Lascaux in the Dordogne comes later, at roughly 17,000 years old. The famous bulls and horses and deer, the swimming stags with their antlers raised above an imagined river. Human handprints pressed in red and black pigment against cave walls across Spain and Indonesia and Australia, some of them older still. The light from Sagittarius A that is arriving at our telescopes now. The radio waves Bruce Balick and Robert Brown first detected in 1974, the infrared photons that gravity and Keck have been gathering for decades. All of it left the galactic center somewhere in that window. Roughly 26,000 years ago, give or take the measurement uncertainty. When it departed, there were no cities, no writing, no wheels, no planted fields. The ice sheets that covered northern Europe during the last glacial maximum had not yet retreated. Mammoths still grazed across what is now Siberia. The human population of the entire Earth was perhaps a few million people, scattered in small bands across most of the world's land masses. And those waves were already on their way to us, already crossing the interstellar dark, already threading through the dust that would have stopped visible light cold, pressing through the intervening gas clouds and the spiral arm structures and the long emptiness between stars on a journey of 26,000 years before arriving, finally, at the collecting mirrors of our telescopes and being turned by our instruments and our mathematics into knowledge. This is what it means to observe the sky. It is not watching the present, it is reading the deep past. Every telescope is a time machine, and the farther you look, the further back you go. Our nearest stellar neighbor, Proxima Centauri, we see as it was 4 years ago. The Andromeda Galaxy appears to us as it was 2.5 million years ago, long before our genus Homo existed on Earth. And the galactic center, our own galaxy's center, the thing that anchors our entire spiral home, we see as it was 26,000 years ago, when our ancestors' art was new, and the ice had not yet melted, and the world was quieter and colder than the one you know. What is happening at the galactic center right now, at this actual moment, as you rest wherever you are? Whatever the real state of Sagittarius A is at this instant, is information that has not yet reached us. It left 26,000 years from now in our future, and it will arrive 26,000 years from now in someone else's future. The now of the galactic center is by definition inaccessible to us. Not because our instruments aren't good enough, not because we haven't tried, but because the universe runs on light speed limits, and 26,000 years of light travel time simply cannot be shortened by any technology or cleverness or desire. Whatever Sagittarius A is doing tonight, we will not know until the year 28,026, approximately. By which point, well, it's a long time. Long enough that the question of what we might be, by then, feels like its own quiet wonder.
I find something genuinely peaceful about that, though I understand if you find it strange. There is something about knowing that the universe simply has this built-in veil, this fundamental and uncrossable horizon of light travel time, that removes a kind of anxiety from the question. We cannot know the present state of the galactic center. We never will know it, not directly, not in any lifetime. So we observe what there is to observe.
We measure what the 26,000-year-old signal tells us, and it turns out that signal, gathered carefully and analyzed with extraordinary skill, tells us quite a lot, more than you might expect. Because here's what the gravity result tells us with that 0.3% precision, and here's what the infrared work at Keck and the VLT tells us in its steady, patient decades of data. The galactic center is not just a location, it is not just a direction, it is a place we have mapped, a place we have measured, a place whose central black hole we know with more confidence and precision than almost any other black hole in the universe, including, in some respects, the black holes that are far closer to us in cosmic terms but are embedded in less favorable circumstances for measurement. The combination of knowing the mass, 4.54 million solar masses, and knowing the distance, 8,178 parsecs to better than 0.33%, and knowing the size of the event horizon, 12 million kilometers in radius, fitting inside Mercury's orbit, gives us a picture of Sagittarius A that is at once precise and strange and humbling. We know it extraordinarily well. We have never seen it directly. We cannot see it now. We are observing its past. And yet the numbers are real, the measurements are solid, the physics is confirmed. How did we get there? How did we go from the discovery of a radio source in 1974 to a Nobel Prize level measurement of the mass and distance of the black hole at the galaxy's center? The short answer is one star. But that star deserves its own chapter of the story, which is coming, because it is genuinely one of the most elegant pieces of observational astronomy ever done. A long, patient, beautiful piece of work that used the simplest possible physics, orbital mechanics that Newton himself would have recognized, and applied it to an orbit so extreme, so fast, so close to the black hole, that it stopped being Newtonian and became Einsteinian. And the place where Newton runs out of steam and Einstein has to take over is exactly where the science gets interesting. For now, though, let's stay with what we have established. We know that the center is hidden in visible light. 30 magnitudes of extinction, 1 photon in a trillion, no optical telescope will ever look through that curtain. We know that infrared light at wavelengths around 2 microns in the K-band passes through far more easily, just 2 to 3 magnitudes of extinction. And this is the window that Keck and the VLT used to see the stars orbiting the invisible center, year after year, building up a picture of a place their cameras had no business being able to observe at all. We know that radio waves pass through the dust entirely, and that it was radio waves in 1974 that first revealed the compact, bright, peculiar source that Bruce Balick and Robert Brown named Sagittarius A star, with Robert Brown's excited asterisk attached to it. And we know the dimensions of what sits there, a black hole of 154 million solar masses with an event horizon 12 million kilometers in radius, fitting comfortably inside Mercury's orbit, located at a distance of approximately 26,000 light-years from Earth, a distance now pinned to better than 0.3%. Better, in proportional terms, than most things in astronomy are ever measured. All of that from invisible light, all of it from patient, careful, decade-long observations in wavelengths your eyes cannot perceive, all of it from a place you have never directly seen and never will. And now the question that has been waiting quietly in the corner of this whole story, the open loop that's been turning slowly since we first started talking about how we know any of this at all. That question is ready to be answered. How do you weigh something you cannot see? The answer is orbit. It is always orbit. If you can watch an object travel around an invisible center, if you can measure how fast it moves and how far from the center it is, and how long it takes to complete one circuit, then the laws of gravity, which are precise and reliable and the same everywhere in the universe, will tell you exactly how massive the invisible thing must be to keep that orbit running. This is not clever trickery, it is just physics. The moon goes around the Earth at a certain speed and distance, and from that you can calculate the Earth's mass. The Earth goes around the Sun at a certain speed and distance, and from that you can calculate the Sun's mass. And if a star goes around Sagittarius A at a certain speed and distance, and with a certain period, you can calculate the mass of the black hole. The problem, the beautiful difficult problem, is that to weigh the black hole this way, you need to actually track the star. You need to watch it complete enough of its orbit to know the orbit's shape. You need to measure its speed and its position precisely enough, over long enough, to pin down the mathematics. And at the galactic center, 26,000 light-years away, hidden behind 30 magnitudes of dust in visible light, that is not an easy thing to do. But two groups of astronomers working independently spent decades doing exactly that. One was based at the UCLA Galactic Center group led by Andrea Ghez. The other was centered at the Max Planck Institute for Extraterrestrial Physics in Germany, led by Reinhard Genzel. Both teams used near-infrared imaging, Keck for the UCLA group, the VLT for the Genzel group, to watch the stars near the galactic center, year after year, measuring their positions with extraordinary care, tracking their motions against the fixed background of the galaxy. And in the data, amidst the crowded, glittering swarm of the nuclear star cluster, millions of stars packed into the few light-years around the center, a stellar metropolis of a density that our own neighborhood cannot begin to match, one star emerged as the key. It was given the designation S2 by the Genzel group. The UCLA team called it S02 in their naming scheme, the 0 indicating it was one of the innermost, the 2 distinguishing it from its neighbors. Both names refer to the same star, and what made this star different from all the others in that crowded central region was something that required years of patient observation to become apparent. S2 was on a tight, fast, highly elliptical orbit around the invisible center. Not a gentle circular drift, but a stretched, elongated ellipse, the kind of orbit that Kepler first described for the planets around our Sun, an oval path with the gravitating object not at the middle, but at one of its two focal points. And S2 swept around that ellipse quickly by stellar standards. Its orbital period, the time for one complete circuit around the center, is approximately 16 years. 16 years, in cosmic terms, that is nothing. A human lifetime spans several S2 orbits. And this meant that by watching the center for 16 years and then for another 16, and then continuing, you could watch one complete orbit unfold in front of you, could see the star swing in from the far side, accelerate as it fell inward, whip around the closest approach, and then decelerate as it pulled outward again, describing the full oval of its path. You could measure not just the direction of motion, but the curvature of the path, the rate of acceleration, the change in velocity as the star dove toward the center and pulled away. The closest approach, astronomers call it pericenter, the point at which S2 comes nearest to the black hole, brought the star to within about 120 astronomical units of Sagittarius A. Keck. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometers. So 120 astronomical units is about 18 billion kilometers, roughly 3 times the distance of Pluto from our Sun. That sounds far in everyday terms, but remember the scale. The black hole's event horizon is at 12 million kilometers. S2 at its closest is at 18 billion kilometers. The star threads through the inner solar system analog in a cosmic sense, passing through what would be the rough equivalent of the outer reaches of our planetary neighborhood before swinging back out. At that pericenter distance, the gravitational pull on S2 is extraordinary, and S2's response to that pull is extraordinary. In May 2018, when S2 made its closest approach, an event astronomers had been anticipating and preparing for years, setting up instruments and allocating telescope time and making sure every data point was captured. The star's orbital speed at pericenter was measured at approximately 7,700 kilometers per second, 7,700 kilometers every second. The speed of light is just under 300,000 kilometers per second, so S2 at pericenter was moving at about 2.5% the speed of light, 2.5%. It is a number that requires a slight pause because we don't have everyday reference points for what that means in terms of felt experience. In 1 second, at that speed, S2 crosses a distance of 7,700 kilometers, approximately the diameter of the Earth. In a single heartbeat, the star moves the width of our entire planet. Nothing in our everyday experience is remotely like this. Our fastest spacecraft at their peak, the Voyager probes, moving at about 17 kilometers per second through the outer solar system, are slower than S2 by a factor of 400. And yet S2 is just a star, a perfectly ordinary young B-type star, the same kind of blue-white stellar object scattered throughout the galaxy, burning hydrogen in its core, doing nothing unusual in its internal physics. It is only its orbital situation. The extraordinary proximity to the black hole, the steep gravitational gradient at the center of the galaxy, that makes its speed so extreme. And at that speed, at that proximity, something else becomes relevant. At 2.5% the speed of light moving through the deepest gravitational well in the local universe, S2 is no longer simply following Newton's laws, it is following Einstein's. But that is the next chapter of the story, and it is one that deserves its own quiet space to unfold. So let's rest here for a moment. You now know how we see the unseeable center, not invisible light. That path is closed, has always been closed by 30 magnitudes of dust and a factor of 1 trillion in attenuation. But in the near-infrared, at 2.2 microns in the K-band, the same dust dims the signal by only 2 to 3 magnitudes, and through that narrow infrared window, the Keck Observatory in Hawaii and the Very Large Telescope in Chile spent decades watching the center's stars move. And in radio, where dust is no obstacle at all, Bruce Balick and Robert Brown found the compact, peculiar, excited asterisk source in 1974 that we now know as Sagittarius A star, the black hole itself. That black hole carries a mass of 4.154 million suns. Its event horizon fits inside Mercury's orbit, 17 solar diameters wide, 12 million kilometers in radius, small, impossibly dense, and dark. It sits at a distance of 26,673 light-years from Earth, measured by the Gravity Collaboration in 2019, to a precision better than 0.3%, the best measurement of that distance in the history of astronomy. And all of this, the mass, the distance, the dimensions, was made possible because of a single star whipping around the invisible center at 2.5% the speed of light, traced and measured and tracked over decades by 2 independent groups of astronomers on 2 different continents, until the orbit was complete and the physics was clear and the answer was certain. That star is S2, and what S2 told us goes beyond just mass and distance. At those speeds, in that gravity, something else happened. Something Einstein had predicted a century earlier from the mathematics of general relativity. Something that had been seen before in our own solar system, in the slow precession of Mercury's orbit around the Sun. The same Mercury whose orbit the event horizon of Sgr A would fit inside. The universe has a way of making elegant echoes. And the echo here is a lovely one. S2 is a young star, a B-type star, the kind astronomers call hot and blue-white, the kind that burns hard and doesn't last long in cosmic terms. It is not especially remarkable on its own. If you pulled it out of the galactic center and dropped it somewhere near our own solar system, you might notice it in a clear, dark sky, a bright point among many, and then move on. It would not arrest your attention. But S2 is not somewhere near our own solar system. It is there at the center, threading an ellipse so tight and so fast around the invisible heart of the galaxy that watching it is like watching a stone on a very short string, swung by something you cannot see at a speed that should not be possible for something made of gas and light. It was first tracked in the 1990s. Both teams, Reinhard Genzel's group working at the Very Large Telescope in Chile and Andrea Ghez's group at the Keck Observatory in Hawaii, began acquiring infrared images of the region around Sagittarius A star, stacking exposure after exposure, year after year, mapping the positions of the stars crowded into that impossibly dense nuclear region. And among all those stars, S2 moved the most. It moved in a way that caught the eye even in early data. A clear arc, a trajectory that was obviously curved, obviously orbital, obviously anchored to something at the center. The question was what? You can't see Sagittarius A star directly. Even in the infrared where the dust is much thinner, the black hole itself gives off little enough light that it doesn't announce itself as a beacon. What you see instead is the effect, the way the surrounding stars move, the way they accelerate, the way they curve along paths that only make sense if something enormous is sitting unseen at the focus of their orbits. The black hole is the invisible string. The stars are how you know it's there. And S2 was the clearest string of all. Both teams tracked it. Year by year, the arc extended, the points on the graph accumulated, and as the arc extended, the shape of the orbit began to emerge. An ellipse, a very elongated ellipse, much more stretched than a circle, the kind of orbit where a star spends most of its time far out in the slow, cold part of its path, and then comes screaming inward at the near end, the pericenter, before hurling itself back out again. The period of S2's orbit is roughly 16 years. 16 years is, in astronomical terms, nothing. It is a blink. Most objects in the outer solar system take longer than that to complete a single circuit. For comparison, Pluto takes about 248 years. But S2, orbiting something 4 million times the mass of the Sun at a distance of only a few thousand astronomical units, completes its loop in 16. The mass that drives it must be extraordinary. The concentration must be extraordinary. The size of the region containing it must be very small, far too small for 4 million solar masses to be, say, a dense cluster of stars. The mass has to be compact, has to be for the physics to work. So as the orbit filled in, year by year, the conclusion was becoming clear. By the early 2000s, both teams had enough of S2's arc to say with confidence, something of enormous mass, extraordinarily compact, is sitting at the center. Something that is, almost certainly, a black hole. But to say almost certainly is not the same as to prove it, and to know the mass is not the same as to know it precisely. What both teams needed was a complete orbit, the full 16-year loop traced from start to end, with enough data points to fit the orbital parameters precisely. They needed to watch S2 go all the way around, so they kept watching. The pericenter, the closest approach, was coming. The point in S2's orbit where it would come nearest the black hole, swing around the inside of that tight ellipse, and then begin its long journey back out. That closest approach would occur in May 2018. By then, the Keck team and the VLT team had been watching S2 for more than 2 decades. They had accumulated hundreds of measurements, positions, velocities along the line of sight, the star's spectrum collected night after night with extraordinary patience. When May 2018 came and S2 made its closest pass, it came within approximately 120 astronomical units of Sagittarius A star. 120 AU. That is the distance from the Sun to a point well beyond Pluto, compressed into a swing around a black hole. And at that closest point, S2 was moving at roughly 7,700 kilometers per second. Sit with that for a moment. 7,700 kilometers per second, that is 2.5% of the speed of light. In a single second, S2 at pericenter crosses a distance greater than the width of the Earth, almost twice over. It is moving so fast that the very nature of space and time begins to assert itself in ways that aren't negligible, ways that Newton's gravity alone cannot fully account for. And that is where Einstein comes in. Actually, Einstein comes in twice, in two separate moments, separated by 2 years, each one more remarkable than the last. The first moment came in 2018, right there at pericenter. When S2 was closest to Sagittarius A star, it was deep in a gravitational field of staggering intensity. And in a strong gravitational field, light does something that Newton never predicted. It stretches. Not because anything is physically pulling the photons apart like taffy, but because of what gravity does to time and space, as Einstein described in his general theory of relativity. Near a massive object, gravity is equivalent to being deep in a potential well. Climbing out of that well costs energy. And for a photon, which carries its energy in its frequency, its color, losing energy means shifting toward lower frequencies, toward the red end of the spectrum. This is gravitational redshift. It had been observed before in various settings, but never quite like this. Never around something as massive as a supermassive black hole, never in such an extreme gravitational field. When S2 was at pericenter and the gravity instrument on the VLT interferometer was watching its spectrum closely, the light from S2 was measurably redder than it should have been based on the star's motion alone. After accounting for the Doppler redshift from the star moving away from us, a residual remained, a deepening of the red that matched almost exactly the gravitational redshift predicted by general relativity for a star at that depth in that field. It was a confirmation not just of S2's orbit but of Einstein's equations, tested against the strongest gravitational environment in our galaxy. The teams published the result in 2018, and then they kept watching. Because S2 came back around, it always does, every 16 years. And as it continued on its orbit, something else was becoming measurable, something subtler, something that requires watching not just one pass, but enough of the orbit to see the whole ellipse shift. An orbit around a massive object is not in Newtonian gravity perfectly static. In classical physics, a planet or a star on an elliptical orbit comes back to exactly the same ellipse each time. The long axis of the ellipse points in the same direction, forever, unless something perturbs it. But Einstein's general relativity adds a correction. In strong fields, the ellipse itself rotates, very slowly, a fraction of a degree per orbit. The long axis of the orbit precesses swinging around so that if you traced many orbits of the same object on a star chart, it wouldn't draw a perfect ellipse closing on itself. It would draw a rosette, a slowly rotating petal shape, like a flower, turned a little more with each circuit. This is Schwarzschild precession. It is named for Carl Schwarzschild, who worked out exact solutions to Einstein's equations very early in the theory's history. And it is the same fundamental effect, the same geometric consequence of curved space-time as the precession of Mercury's orbit. Mercury precesses by a tiny amount each century, about 43 arc-seconds per 100 years, a discrepancy that puzzled astronomers for decades before Einstein's general relativity explained it perfectly in 1915. It was one of the early triumphs of the theory. The solar system's innermost planet, its orbit rotating at a rate that only curved space-time could explain. It was beautiful. And now S2, the galactic center's innermost closely watched star, showed the same effect. In a much stronger field, over a shorter baseline, but the same fundamental geometry. The Gravity Collaboration published their detection of S2's Schwarzschild precession in 2020. The orbit's ellipse was rotating, slowly, measurably, in exactly the way Einstein had predicted. The same rosette pattern, the same physics, tested now not around our modest sun but around a black hole 4 million times more massive, 26,000 light-years away, in the most crowded stellar environment in the galaxy. 2 tests, 2 passing grades, from a star that most people have never heard of, in a part of the sky that cannot be seen in ordinary light. There is something deeply satisfying about that. The universe being caught once again doing exactly what the equations said it should. The math written down more than a century ago, and the sky, in 2018 and 2020, quietly agreeing. By the time 2020 arrived, the case was not just compelling, it was unassailable. That year, the Nobel Committee in Stockholm looked at everything. 2 decades of star tracking, the complete orbit of S2, the gravitational redshift, the precession, the mass measurement, the distance measurement, and awarded the Nobel Prize in Physics. 1/2 of the prize went to Roger Penrose, the British mathematician and physicist, for theoretical work of a different kind. Penrose had, back in 1965, used rigorous mathematics to prove something profound: that the formation of black holes is a robust, unavoidable prediction of general relativity. Not a mathematical curiosity. Not a special case. If general relativity is correct, which and all the evidence says it is, then black holes are not merely possible, they are inevitable in the right circumstances. Penrose gave the theory its foundations, proving that once matter collapses past a certain point, nothing can stop the singularity from forming. It was one of the cornerstones of modern theoretical physics. The other half of the 2020 Nobel Prize went to Reinhard Genzel and Andrea, Ghez, jointly, for the discovery through decades of observational work of a supermassive compact object at the center of our galaxy. Reinhard Genzel had led the effort at the European Southern Observatory's Very Large Telescope in Chile, developing the gravity instrument and the Sharp and Lascaux cameras before it, building the team and the technology and the patience that the work demanded over more than 20 years. Andrea Ghez had led the Keck Observatory program in Hawaii, pioneering the use of adaptive optics to sharpen infrared images and remove the blurring that Earth's atmosphere introduces, extracting precise measurements from a region so crowded and so distant that the task had seemed nearly impossible when she began it in the 1990s. They had worked independently, they had sometimes competed, and they had, step by step, converged on the same conclusion, using different instruments on different mountains in different hemispheres, watching the same stars move in the same gravity. Andrea Ghez became the 4th woman in history to win the Nobel Prize in Physics. The first was Marie Curie in 1903, more than a century earlier. The second was Maria Goeppert-Mayer in 1963 for her work on the nuclear shell model. The third was Donna Strickland, who won in 2018 for her work on ultrafast laser pulses, just 2 years before Ghez. 4 women across the entire history of the prize, and Ghez among them, for standing on a mountain in Hawaii and watching a single star orbit something invisible, year after year, until the picture was undeniable. Now let's stay with something for a moment, because it's worth unpacking fully, gently, because it's one of the most remarkable things about this whole enterprise. We opened a question earlier, in the soft silence before this section began. How do you weigh something you cannot see? It is a question that sounds almost philosophical. If the black hole at the center of our galaxy is invisible, buried behind 30 magnitudes of dust in visible light, emitting no light of its own in any wavelength, fundamentally dark. Then how on Earth, or rather, how in the universe, do you know how heavy it is? The answer is the orbit. When any object moves under the influence of gravity, the shape of its path and the speed with which it moves along that path are determined by the mass doing the pulling and the distance between them. This is Kepler's third law, one of the foundational discoveries of astronomy from the early 17th century. The period of an orbit and its size are related to the central mass in a precise mathematical way. You don't need to see the central mass. You only need to measure the orbit of something going around it. If you know the period, how long one complete loop takes, and you know the size, specifically the semi-major axis of the ellipse, then you can solve for the mass. It is a calculation, a beautiful, direct calculation. For S2, both teams spent years measuring exactly those quantities. The period, about 16 years, now known precisely. The orbital size and shape, mapped point by point from infrared imaging, refined year by year, constrained by hundreds of measurements of the star's position and velocity. And from those quantities, the period and the semi-major axis, combined with the known laws of orbital mechanics, you can compute the mass of Sagittarius A star directly. The answer is approximately 4.54 million solar masses, according to the Gravity Collaboration's 2019 analysis. 4,154,000 suns concentrated into a region you could fit inside the orbit of Mercury. And the distance? The distance falls out of the same geometry. The orbit of S2 has angular size when projected on the sky. The measurements of position are in arcseconds, the tiny angular units astronomers use to measure how far apart things appear. And the orbit also has a physical size in astronomical units that follows from Kepler's laws. If you know both, the angular size and the physical size, you can calculate the distance the same way you might estimate how far away a ruler is by knowing how long a ruler is and how big it appears. The Gravity Collaboration's 2019 result, 8,178 parsecs, which converts to approximately 26,673 light-years, with an uncertainty of less than 0.3%, less than 0.3%, a precision that would have seemed fantastical to astronomers working even 20 years earlier when the distance to the galactic center carried an uncertainty of roughly 10%, meaning the true value could have been anywhere in a range of several thousand light-years. Now they know it to within a small fraction of that range, better than 0.3%, because of one star's orbit. It is worth pausing to appreciate the elegance of this. The galactic center is 26,000 light-years away. The dust between here and there blocks visible light so thoroughly that no optical photon from the core reaches Earth. The black hole itself emits nothing you could call a simple observation. The whole region is, by any ordinary standard, inaccessible. And yet, by watching a star orbit over 16 years through infrared detectors on ground-based telescopes, human beings determined the mass of the central black hole to a few percent, and the distance to a fraction of a percent. There is something in that. Something about the indirectness of knowledge, about how much you can learn from the movement of what you can see rather than from looking directly at what you cannot. That is, I think, one of the quietly wonderful things about modern astronomy. The universe hides its most extreme objects, and we find them anyway. We find them in shadows, in motions, in spectra, in the curvature of orbits around dark centers. S2 didn't know it was orbiting anything remarkable. It didn't know that its path through the galactic center was being recorded by two separate groups of humans on a small planet 26,000 light-years away. It just moved, as things move, pulled by gravity, following the ellipse that the geometry of the field around it demanded. And we watched. We watched for 20 years. And from that watching came a Nobel Prize and a mass and a distance, and two confirmations of general relativity in one of the most extreme environments in the observable galaxy. It is a long return on 20 years of patience. But then the galactic center is not a place that rewards haste. Something else is worth sitting with quietly because it has been there in the background of this whole story, and it deserves to come forward now. All of those measurements, the infrared positions of S2, the velocity data from spectroscopy, the confirmation of gravitational redshift in 2018, the Schwarzschild precession in 2020, all of that was collected using light that traveled from the galactic center to our detectors. Light that took 26,000 years to make the journey. Think about what that means for the measurements themselves. When the gravity instrument at the VLT recorded S2's spectrum in 2018, catching the gravitational redshift as S2 swung through pericenter, the pericenter passage it was recording did not happen in 2018. It happened 26,000 years ago. S2 made that closest approach to Sagittarius A star roughly 26,000 years before the data were collected. The confirmation of Einstein's gravitational redshift at the galactic center was published in 2018, but the physical event that produced the data occurred in the deep past, when the ancestors of every human alive today were navigating their world with stone tools and ochre, and the kind of darkness that we have largely forgotten now, sleeping under skies more crowded with stars than most of us will ever see. The orbit we tracked is a historical orbit. The precession of S2's ellipse that gravity detected in 2020, that slow rotation of the rosette, was happening 26,000 years ago, and the light carrying evidence of it has been traveling toward us ever since. The Nobel Prize-winning observation is, in a precise sense, a study of ancient history. This does not make the measurements less valid. The laws of physics are not different 26,000 years ago than they are today. Einstein's equations work then as they do now. Gravity at the galactic center, 26 millennia in the past, follows the same rules as gravity at the galactic center in this moment. So confirming general relativity from that data is still genuine science, still a real confirmation, still enormously meaningful. But it adds a layer of strangeness that is easy to pass over if you're not paying attention. We know the mass of Sagittarius A star, we know its distance, we know its orbit geometry, we know that 26,000 years ago it was confirming Einstein, and we know essentially nothing about what it is doing at this moment. Nothing. Because the light from this moment, whatever Sagittarius A star is doing right now, tonight, in whatever counts as now at the galactic center, that light will not arrive here for another 26,000 years. There is a now at the galactic center in some meaningful physical sense. Things are happening there. S2 is somewhere in its 16-year orbit. Sagittarius A star is presumably still there. Still 4 million solar masses of compressed dark gravity, still occasionally flaring, still pulling the stars of the nuclear star cluster along their paths. The universe at the galactic center is, in all probability, ongoing. We just can't know any of it. Not yet. Not for a very long time. 26,000 years from now, the light leaving the galactic center in this moment will arrive. And whatever humans or their successors or whatever minds exist to receive it will learn what was happening there tonight, whether anything changed, whether Sagittarius A star fed or flared, or a star fell in closer than S2 has ever come, whether anything at the center was different in any measurable way from what it was when the data we just discussed were produced. We will not know. And there is something genuinely profound about that limitation. Not as a failure, not as a gap to be embarrassed about, but as a feature of the universe itself. The universe is large. Light is fast, but not infinitely fast. Distance imposes delay, and delay imposes a kind of epistemic horizon. Beyond a certain point in space, you cannot know the present. You can only know the past. The galactic center is not beyond that epistemic horizon in the absolute sense. It is not at a cosmological distance, not receding from us, not hidden behind the edge of the observable universe. The light from there reaches us in time, but it reaches us on a delay of 26,000 years, and that delay is, from the perspective of any individual human life or any human civilization, we have so far managed to build or imagine, essentially forever. When the light now arriving from the galactic center set out on its journey, there were no cities, no writing, no agriculture, no wheels, no metal, no bread. The last of the Neanderthals may still have been alive. The first humans to cross certain stretches of land were still walking. The global population of Homo sapiens was perhaps a few million people, spread thin across the world, living in ways that would be almost entirely unrecognizable to us now. And somewhere in that same ancient moment, S2 was swinging through its pericenter, climbing out of the gravitational well of Sagittarius A star. The photons of that gravitationally redshifted light beginning their long arc toward a planet that didn't yet know it was waiting for them. That is what we actually measured. That is the data. That is, in a very real sense, what astronomy is, the systematic study of light that left its source before the observers were born. In some cases, before their species existed. It is a strange business when you look at it directly, but it is also, when you let it settle, a deeply beautiful one. We are receivers. We sit on this small planet at the edge of a spiral arm, and we collect the light that the universe has been sending, and we read what it says. The messages are old, sometimes very old, but they are real and they are precise, and they carry genuine information about genuine physics happening in genuine places. And S2 sent us something important. It sent us the shape of its orbit, the speed of its passage, the stretching of its light, the rotation of its ellipse. It sent us enough to weigh the dark thing at the center of our galaxy, to pin down our distance from it, and to confirm that the mathematics of general relativity holds not just around our modest sun, but in the most extreme gravitational environment within 26,000 light-years of where you are lying right now. That is not nothing. That is, in fact, quite extraordinary. And it happened because two groups of astronomers on two different continents built infrared detectors sensitive enough to distinguish individual stars in one of the most crowded regions of sky in the galaxy, and then had the patience to watch those stars year after year for longer than some careers last, until the orbit was complete and the picture was clear. Genzel and Ghez did not get lucky. They got precise. Precision in the data and patience in the accumulation of it, and then the rigor to extract from the orbit's geometry everything the orbit had to say. And S2 had quite a lot to say. Here is something that is easy to miss in all of this, something that quietly makes the whole story stranger. S2 is a young star. It is a B-type star, as we mentioned, young and hot and blue-white, the kind of star that burns through its hydrogen fuel quickly, cosmically speaking, living a much shorter life than our own sun. The sun will likely last another 5 billion years. A star like S2 has a life measured in hundreds of millions of years at most, sometimes tens of millions. And S2 is near the center of the galaxy. Very near. Its orbit keeps it in the vicinity of Sagittarius A star on a permanently close trajectory. No gentle suburban distance, no quiet outer spiral arm. It lives, and presumably formed, in one of the most hostile stellar environments in the galaxy. This is a problem. Forming a star requires gravity to pull a cloud of gas and dust together slowly. overcoming the cloud's own internal pressure until the material becomes dense enough for nuclear fusion to ignite at the center. It is a delicate process that benefits from time and relative calm, and the vicinity of a 4 million solar mass black hole is not calm. The tidal forces near Sagittarius A star, the difference in gravitational pull between the near side and the far side of any given gas cloud, are so extreme that they would tend to rip a forming star apart before it could consolidate. The very gravity that makes the region so interesting should, by straightforward analysis, prevent stars from forming there at all. And yet, S2 is there, young and bright and orbiting. And it is not alone. The S stars as a group, this cluster of fast-moving young stellar objects on tight orbits around Sagittarius A star, include several other hot, young, massive stars that have no obvious right to exist where they do. This is what astronomers call the paradox of youth. Young stars in old, hostile places, stars that form where formation should be impossible. The leading explanation is that they formed somewhere else, perhaps in a dense disk of gas that briefly surrounded the black hole, a kind of ring of material in which the local self-gravity was strong enough and the conditions compact enough to trigger star formation despite the tidal environment. This would be in situ formation in a transient accretion disk, and it would explain both the youth and the tight orbits. The stars formed where the disk was, and as the disk evolved and dissipated, the stars remained. But it is still, at the time the light we're studying left on its journey, an active area of research. An open question. We think we understand this, but we're not entirely certain. And that is fine. That is how science works. Not every question is answered simultaneously with every other. S2 gave us the mass and the distance and the relativistic tests. The question of how it and its siblings came to be there remains, delightfully, not quite closed. The universe is generous with its puzzles. It gives you one answer and opens a door to two more questions. The Galactic Center, for all that we have learned about it, through 20 years of orbit tracking, through Nobel Prizes and relativistic confirmations, through infrared detectors and radio interferometry, and the slow, accumulated patience of two groups of astronomers on two different mountains, is still, in meaningful ways, a place of ongoing mystery. We know how heavy the thing at the center is, we know how far away it is, we know what one of its stars does over 16 years, and we know that Einstein's mathematics describes what we see. We know the distance of the journey the light makes, 26,000 light-years from the center to our detectors, carrying information 26,000 years old. And there is still quite a lot we do not know. There is still the question of what is happening there right now. There are still the other S stars in their tight orbits, some of them even faster than S2. There is still the nuclear star cluster with its millions of stars crowded into a few light-years, and the question of what else might be lurking in that dense stellar city. There is still more to explore, and perhaps the most dramatic chapter in that ongoing exploration arrived on the 12th of May 2022. That was the day the Event Horizon Telescope collaboration released the first image of Sagittarius A itself. Now, when I say image, I want you to hold that word gently for a moment, because we are going to have to renegotiate what it means, because what the Event Horizon Telescope produced is not an image the way a photograph is an image. It is not the way you take a picture of a flower or a mountain or a face. Your phone camera captures visible light bouncing off a surface and focuses it through a lens onto a sensor. That is photography. What the Event Horizon Telescope did is something quite different, and understanding the difference is part of understanding why this achievement took so long and why it means what it means. The Event Horizon Telescope is not a telescope in the ordinary sense. It is not a single dish pointed at the sky from a single mountaintop. It is a network a collaboration of radio observatories spread across the entire surface of the Earth, from Hawaii to Chile to Greenland to the South Pole, all pointed at the same target at the same time, all collecting the same radio waves, all synchronized to atomic clocks accurate to a tiny fraction of a nanosecond. The data from every observatory is recorded onto hard drives, thousands of them, and those hard drives are then physically flown to a processing center because the data is too vast to transmit over the internet. And then, through a technique called very long baseline interferometry, the signals from every observatory are combined and cross-referenced and processed by algorithms running for months, and out of that vast mathematical operation, a picture emerges, not a photograph, a reconstruction, a map built from mathematics, from the interference patterns of radio waves gathered from the four corners of the world, translated into something a human eye can look at. The image is false-colored. The radio waves Sagittarius A emits are at a wavelength of about 1.3 millimeters, which is nowhere near visible light. Your eyes would never perceive it. To show you the image at all, the scientists assigned colors to the intensity of the radio emission. The bright orange and yellow ring you have likely seen represents the hottest, brightest regions of gas orbiting the black hole. The dark center is the shadow, the region where the black hole's gravity is so extreme that even radio waves cannot escape. And that shadow is extraordinary. It spans roughly 52 micro-arc seconds. That is a unit so small it is almost beyond picturing. A micro-arc second is 1/millionth of 1/3600th of 1 degree. To give you a sense of what 52 micro-arc seconds actually is, it is comparable to resolving a donut sitting on the surface of the moon. From Earth, a donut on the moon. The Event Horizon Telescope resolved that. It had to because Sagittarius A's is not large on the sky, despite being 4 million times the mass of the Sun. It is simply too far away, 26,000 light-years, and too physically compact, with an event horizon of only about 12 million kilometers in radius, to look like anything at all without an instrument of almost incomprehensible precision. And that image, that orange ring with its dark heart, is consistent with everything we know. The shadow's size matches what you would predict for a black hole of roughly 4 million solar masses at a distance of roughly 26,000 light-years. It is a conformation built from radio waves processed through mathematics, translated into color, of the thing that S2's orbit already told us was there. But why 2022? The Event Horizon Telescope collaboration had already released a black hole image in 2019, the famous first image of the black hole at the center of a galaxy called M87, a giant elliptical galaxy in the Virgo cluster. That image came first, and you might reasonably wonder, if they could image M87's black hole in 2019, why did it take until 2022 for Sagittarius A house, which is vastly closer? The answer is one of the stranger and more delightful complications in modern astronomy, and it comes down to time. The black hole at the center of M87, called M87 Tate, is roughly 6.5 billion times the mass of the Sun. It is a colossus, millions of times more massive than Sagittarius A. And because it is so massive, it is also physically enormous. The gas and plasma swirling around M87 kinks take days to complete a single orbit. The source is, in astronomical terms, slow. When the Event Horizon Telescope spent several nights gathering radio waves from M87 Keen, the target stayed relatively stable. What was there on night 1 was more or less still there on night 2. The image did not blur from the source changing beneath the observation. Sagittarius A is a different problem entirely. Sagittarius A is far less massive, 4 million solar masses versus 6.5 billion, and because of that, the region just outside its event horizon is much smaller. The gas orbiting close in completes a full orbit not in days but in minutes. In the time it takes you to brew a cup of tea, the material nearest the event horizon has gone all the way around, and that means the source is changing, brightening, dimming, shifting, on timescales shorter than a single observing session. Imaging Sagittarius A with very long baseline interferometry is, as several of the scientists on the project put it, rather like trying to take a sharp photograph of a hummingbird's wings. The subject will not hold still. Getting the image required sophisticated new techniques, new algorithms, new ways of averaging and accounting for the source's variability during observation, new computational approaches to reconstructing a picture from a target that kept changing while they were looking at it. It was solvable, it took time, and on the 12th of May 2022, they showed what they had built. So there it is. The first image of our galaxy's central black hole, not a photograph, not something your eyes could ever have seen directly. A radio reconstruction, false-colored, drawn from 1.3 millimeter waves gathered by a planet-sized virtual telescope, its shadow spanning 52 micro-arc seconds. A donut on the moon, consistent with a mass of 4 million suns, at a distance now pinned more precisely than almost any other object in the sky. And the light in that image, the radio waves, the emission, left the galactic center 26,000 years ago. Before the Lascaux paintings, before the handprints on the cave walls, before your ancestors had any way of knowing that they were orbiting something like this, that at the heart of the faint, cloudy river they saw stretching across their night sky, there was this. But the image, remarkable as it is, shows you the black hole. It does not quite show you the neighborhood, and the neighborhood is extraordinary in its own right, because Sagittarius A does not sit alone. Around it, within just a few light years, is one of the densest stellar environments in the entire galaxy. Astronomers call it the nuclear star cluster, and dense is almost too mild a word. In our corner of the Milky Way, the Sun's neighborhood, where we have lived for the last 4.5 billion years, space is largely empty. The nearest star to our Sun is Proxima Centauri, and it is about 4 light-years away. 4 light-years of almost nothing. The stars in our neighborhood are sparsely scattered like a few grains of sand spread across a large room. Near Sagittarius A, the situation is reversed almost beyond imagining. The star density in the nuclear star cluster reaches millions of stars per cubic light-year. Not a few grains of sand in a large room. More like a room packed so tightly with sand that you cannot move. Stars crowded together at separations that in our neighborhood would be unthinkable. And what that means, if you let yourself picture it for a moment, is this. If there were a planet orbiting one of those inner stars, not close to Sagittarius A itself, just somewhere in that dense stellar city, the night sky from that planet would look nothing like ours. We have a night sky with a few thousand stars visible to the naked eye, none of them brighter than a small lamp at arm's length. A planet in the nuclear star cluster would have thousands of stars brighter than our full moon, not faint specks, blazing lights, a night that was never quite dark. A sky so crowded and bright that the concept of night might not even feel meaningful in the same way. It would be an extraordinary place to be if you could be there. And within this dense stellar crowd, there is a subset of stars that have commanded particular attention. The S stars. S2 is the one we have already spent so long with. The 16-year orbit, the 7,700 km per second sprint, the gravitational redshift, the Schwarzschild precession, the Nobel Prize's beating heart. But S2 is not alone. There is a whole population of these stars, young and bright and on tight orbits, and some of them are even more extreme. S62 is one. Another of the inner S stars in a tight orbit around the central black hole, one of the many objects catalogued by the teams watching this crowded region. And then there is S474. S4714 has been clocked at Pericenter, its closest approach at speeds of up to roughly 24,000 kilometers per second. That is approximately 8% of the speed of light. 8%. S2, which we spent so long marveling at, reaches about 2.5% of the speed of light at its closest. S4714 is more than 3 times faster. It is, by that measure, among the fastest known stars in the entire galaxy. A star moving at 8% the speed of light, rounding the corner of a 4 million solar mass black hole. If you could somehow stand on a planet and watch S4714 pass at its nearest point, it would cross the sky at a speed that makes S2 look leisurely. These stars, S2, S62, S4711, S47 Baitor, and the others catalogued by the Keck Observatory's team and the Gravity Collaboration, are all classified as B-type stars, young, hot, massive, bright. And their presence so close to Sagittarius A presents what astronomers have come to call the paradox of youth, because these stars should not, by the usual rules, exist where they are. Star formation requires dense clouds of gas to collapse under gravity slowly over millions of years. But the tidal forces of a supermassive black hole are violent. They shear gas clouds apart before they can collapse and form stars. The gravity is too strong, too differential between one side of a cloud and the other. It should tear a collapsing cloud to pieces before any star can ignite. And yet, there they are, young stars on tight orbits, right next to the black hole. The physics that should prevent them from forming, apparently, did not get the memo. The leading explanation is that they formed not from quiet collapsing clouds in open space, but from a dense accretion disk, a swirling, compressed disk of gas and dust circling the black hole closely enough to reach the densities required for collapse despite the tidal disruption. Self-gravity within the disk might have been enough to locally overwhelm the tidal forces and birth stars in that extreme environment. But this remains an active area of research. It is another one of those open questions at the Galactic Center. Another door opened by learning something else. The paradox of youth may have an answer, or it may have several competing answers, or it may have an answer we have not quite reached yet. For now, it sits in the column of things we are still working out. And meanwhile, at the center of all this, at the center of the dense, stellar city and the tight S-star orbits, and the centuries of observations and the Nobel-winning mathematics, and the planet-wide radio reconstruction, Sagittarius A itself sits quietly, remarkably quietly, for something that massive. A black hole of 4 million solar masses accreting gas and dust at the center of a galaxy is theoretically capable of being extraordinarily luminous. There is a theoretical upper limit on how brightly a black hole can shine, called the Eddington luminosity, which is the luminosity at which the radiation pressure from the infalling material pushing outward balances the gravitational pull inward. At that limit, the black hole is blazing, an active galactic nucleus, a quasar, something bright enough to outshine an entire galaxy of stars. Many black holes in the early universe were operating near or above that limit. Sagittarius A is not. Sagittarius A is, by the standards of supermassive black holes, essentially fasting. It is radiating at a tiny fraction of its theoretical maximum, not 10%, not 1%, but something far smaller, far below what you would expect from a black hole of its mass sitting at the center of a large spiral galaxy with stars and gas all around it. It is, in the vocabulary of astronomers, a low luminosity active galactic nucleus, or sometimes, more simply, a sleeping giant, starving, quiet, not doing much. Most of the time. Because occasionally it wakes up a little, Astronomers monitoring the galactic center in infrared and X-ray wavelengths have observed flares from Sagittarius A, brightenings that last for hours, sometimes shorter, in which the emission increases by factors of several before fading back to its baseline quiet. These flares are thought to come from clumps of gas and material spiraling close to the event horizon and releasing energy as they fall in, or perhaps from reconnection events in the magnetic field lines threading the plasma near the black hole. The exact mechanism is still being investigated, but the flares are real, they are observed, and they are a reminder that the quiet giant at the center is not entirely inert. It stirs, occasionally, and then settles again. It was also, at some point in the past, less quiet than it is now, much less quiet. Because in 2010, astronomers using NASA's Fermi Gamma Ray Space Telescope made a discovery that changed the way we think about the history of the galactic center. They found something enormous that had been hiding in plain sight, largely because it required gamma ray eyes to see it. Above and below the plane of the Milky Way, extending outward from the galactic center, they found two vast structures, bubbles of gamma ray emission, symmetrically placed, one above and one below. Each one extends roughly 25,000 light-years from the galactic plane, 25,000 light-years each bubble. Together they span a total of about 50,000 light-years from tip to tip, comparable to half the diameter of the entire Milky Way disk. These are not small structures, they are enormous, and they are called the Fermi bubbles. What are they? They are, in the current best understanding, the fossilized remains of a past outburst from the galactic center, a time somewhere between millions and tens of millions of years ago when Sagittarius A was not quiet and starving, but actively feeding, perhaps heavily, perhaps in a period of intense accretion that sent vast jets or winds of energy blasting outward through the halo of the galaxy above and below the disk. The gas and plasma pushed outward by that ancient outburst eventually formed these enormous cavities, glowing in gamma rays, preserved in the halo like the rings of a tree preserving a record of the past. The galactic center that is quiet and low luminosity today was, at some point in the not infinitely distant past, a much more energetic place. How long ago the outburst happened, exactly how powerful it was, whether it was one event or many, these are questions still being refined. But the Fermi bubbles are the evidence, the archaeological record, written in gamma rays and extending across half the width of the galaxy. A fossil burp, enormous and symmetrical, from a time when the heart of the Milky Way was alive in a way it no longer is. And then there was the more recent visitor. In 2013 and 2014, astronomers tracked an object called G2 as it made a close pass by Sagittarius A. G2 had been identified a few years earlier as a cloud of gas, a dense, compact cloud drifting through the galactic center on an orbit that would bring it very close to the black hole. Predictions were made. Some models suggested that when G2 approached closely, the tidal forces of Sagittarius A would tear it apart, and the disrupted gas would eventually spiral in and feed the black hole, triggering a significant brightening, perhaps a dramatic flare, perhaps a more sustained increase in activity. There was considerable interest in what might happen. What actually happened was rather more anticlimactic and rather more interesting scientifically. G2 passed close to Sagittarius A and survived. Largely intact, it was stretched and distorted by the tidal forces, as you might expect, but it did not disintegrate into an infalling rain of gas, the way some models had predicted. Sagittarius A did not produce the expected spectacular flare. The source remained more or less its usual quiet self, and the interpretation that gained traction was that G2 might not simply be a gas cloud, it might be a cloud of gas and dust enshrouding a star, a dusty stellar object with a stellar core dense enough to resist disruption. If G2 has a star at its heart, That would explain why it held together. The gravity of the star binds the envelope together even as the black hole tries to pull it apart. A pure gas cloud without that gravitational anchor would not have survived. A cloud wrapped around a star might. It is another open question. What exactly G2 is, whether it hosts a star, what the 2014 passage actually told us about the environment near Sagittarius A. These are threads still being pulled on, but what we know is this: an object many astronomers expected to be dramatically torn apart and consumed by the central black hole made it through and kept going. The galactic center surprised us again. It tends to do that. And somewhere in the midst of all of this, the dense stellar cluster and the S-stars and the sleeping giant and the fossilized outburst and the surviving gas cloud, there is us. Here, 26,000 light-years away, going around. That is perhaps the strangest and most humbling fact of all to sit with quietly in the dark. We orbit the galactic center. Every single one of us, and the Earth, and the Moon, and the Sun, and every planet in our solar system, we are all in orbit around Sagittarius A, circling that quiet 4 million solar mass dark heart at the center of our galaxy. We complete that orbit at a speed of roughly 220 to 230 kilometers per second. That is not 220 kilometers per hour. It is 220 kilometers per second, fast enough to cross the continental United States in about 20 seconds. And even at that speed, the orbit is so enormous, the circumference of a circle 26,000 light-years in radius, that it takes roughly 225 to 250 million years to go around once. Astronomers call this interval a galactic year, one lap around the center, and the last time the solar system was in the same position in its orbit that it occupies tonight, the dominant animals on this planet were not humans. They were not even mammals. The last time Earth was here, in this place in its galactic orbit, dinosaurs were only just beginning to appear. That was approximately 1 galactic year ago. Since the first dinosaurs, since Pangaea was still breaking apart and the continents were still rearranging themselves, we have made one lap. And Sagittarius A has been there at the center the whole time. Quiet, occasionally stirring, surrounded by its dense city of stars. And yet for all that time, for all those millions of years of orbiting, the creatures on this planet had no idea. For the vast majority of the history of life on Earth, the galactic center was simply part of the dark river of stars stretching across the night sky. Not understood, not known to contain a black hole, not known to have anything at all remarkable at its heart. Just a bright patch in the direction of Sagittarius, somewhat brighter than the rest of the band, and behind it, invisible, hidden, sealed away behind 30 magnitudes of dust. The most extraordinary object for thousands of light years in any direction. We have only known what is there for a handful of decades. The radio signal that told us something unusual occupied the center, the discovery by Bruce Balick and Robert Brown in 1974, is not quite 50 years old. A cosmic eye blink, the orbit tracking, the Nobel Prize, the Event Horizon Telescope image. These are the work of people who are alive today, or who were alive very recently. This knowledge is new. Geologically, astronomically, it is brand new. We went from there seems to be an unusual compact radio source at the galactic center, to we have imaged its shadow and confirmed its mass to a fraction of a percent in the space of about 50 years. The span of a human lifetime. That is worth sitting with. And then there is the other piece of it, the piece that I find the most genuinely strange to contemplate, the piece that gives the title of tonight's journey its real meaning. Whatever is happening at the galactic center right now, or this moment as you listen, we cannot know. No one alive can know. No one who will ever live can know, not for another 26,000 years. The light and radio waves and infrared emission we collected to make every observation described tonight, the Keck tracking of S2's orbit, the VLT and gravity measurements, the Event Horizon Telescope's 2022 image, all of it was emitted from the galactic center 96,000 years ago, before the Lascaux caves were painted, before the hand stencils at Chauvet were pressed into the rock, while your ancestors were still in the upper Paleolithic, still learning the shapes of the animals around them, still figuring out how to record what they saw. The light we are analyzing today was already on its way. It had already left. It had already begun its 26,000-year crossing of the galaxy to reach our detectors. When that light left, Sagittarius A was doing something. What exactly, we have no way of knowing, because the light that carries the answer to that question will not arrive for another 26,000 years. The now of the galactic center is, by definition, unknowable to us. We are always looking at the past. We are always seeing a snapshot, a deep time snapshot, tens of thousands of years stale, of a place we cannot reach and cannot observe as it currently is. The galactic center we know is the galactic center as it was. And the galactic center as it is, this moment, this night, that is sealed away from us as surely as if there were a wall between us and it. Except the wall is not made of stone or metal. It is made of time. And light moving through it at the only speed light ever moves, covering the 26,000-year journey at 299,792 kilometers per second, unable to arrive sooner, unable to bring us news any more recent than the Paleolithic. We know Sagittarius A as it was during the last ice age. We know it as it was when mammoths walked and cave bears wandered, and your ancient ancestors painted on walls by firelight, looking up at the same faint band of the Milky Way that you might see tonight, from a dark enough field, having no idea what was at its heart. And what we know about that ancient version of the galactic center, that 26,000-year-old version that is the only version we have ever seen, or ever will see, we know with extraordinary precision. The distance, 8,078 parsecs, better than 0.3% uncertainty. The mass, roughly 454 million solar masses. The orbit of S2, a 16-year ellipse confirmed to match Einstein's mathematics within the errors. The size of the shadow, 52 micro-arcseconds, consistent with everything we predicted. We have measured a place we cannot see in visible light across a distance that makes every human journey in history look like a step 26,000 years into the past, with more precision than almost any other object in the cosmos. That is, if you think about it, one of the most astonishing things that our species has ever done. We found Sgr A not with eyes, but with radio receivers. We weighed it not by visiting it, but by watching one star go around it 16 times. We confirmed the mathematics of general relativity at its edge, not by going there, but by measuring the color of a star's light stretched by gravity. We imaged its shadow, not with a camera, but with a planet-sized array of synchronized radio dishes and months of computation. We found the ghost of its past appetite not at the center itself, but in two enormous bubbles of gamma rays extending above and below the galaxy's disk, preserved for millions of years in the halo. We discovered the paradox of how it has young stars nearby by the simple patient act of tracking their positions year after year through near-infrared filters on mountain-top telescopes. We did all of this without ever going there, without ever sending a probe, without ever collecting a single photon of visible light from the core. We did it through ingenuity and mathematics and decades of careful looking in wavelengths of light that our eyes cannot perceive, and through the accumulated patience of two teams of astronomers who who spent their careers watching one star trace one orbit, and through the collected effort of radio observatories on 6 continents, all pointed at the same patch of sky. And what we found is this. At the center of the galaxy you live in, there is a black hole 4 million times the mass of the Sun, smaller than Mercury's orbit, surrounded by millions of stars crowded into a few light years, orbited by young, fast stars that should not exist near it but do. Quiet and low luminosity today, but once, millions of years ago, energetic enough to blast structures half the size of the galaxy above and below the plane. And it is 26,000 light-years away, which means everything we know about it is a message from the deep past, a letter that took longer to arrive than our entire recorded history, received and read by creatures who have been asking what is at the heart of things for as long as they have been creatures at all. You have never seen the center of the galaxy as it actually is. No one has, no one can, but you now know what is there as it was when the light left. And that is not nothing. That is, in fact, extraordinary. Close your eyes for a moment, if they are not already closed. Wherever you are, whatever corner of the world you are in tonight, whatever time the clock says, whatever the sky looks like above your ceiling, you are sitting on a planet orbiting a star, orbiting a black hole, inside a galaxy that has a heart. You have spent this long evening learning to see in a new way. The dust is in the way, and the distance is in the way, and time is in the way, but you know it is there. You know how heavy it is and how far it is, and what one of its stars does over 16 years. You know that the image you might have seen on a screen, that orange ring with the dark center, was assembled from radio waves by a planet-sized telescope and colored in by human hands to make the invisible something your eyes could hold. And somewhere, 26,000 light-years from wherever you are right now, Sagittarius A is doing something. What we will not know for another 26,000 years. Perhaps it is quiet, as it has been in the recent past. Perhaps the G2 object or something like it has fallen in and stirred a flare. Perhaps there has been some change in the flow of gas into the nuclear star cluster, some shift in the conditions near the event horizon, something that would look different from the way it looked when the light we collected left its source all those millennia ago. We will not know. Our descendants, tens of thousands of years from now, will receive the news. We get only the past. And that is somehow not a limitation to mourn. It is simply the nature of looking at things across vast distance, the nature of a universe where information cannot travel faster than light, the nature of being small and finite and here, in this particular place, at this particular moment. The 26,000-year delay is not a failure of our instruments. It is the universe's honest accounting of how far away things are. And from 26,000 light-years from inside the dense interstellar dust that fills the galactic plane, from the wrong wavelength of light with instruments that did not exist 50 years ago, from a small planet orbiting an unremarkable star on a quiet spiral arm, we found it. We measured it. We weighed it. We watched one of its stars complete its orbit and confirmed that the geometry of space itself bends exactly as Einstein said it would, right there at the edge of 4 million solar masses. That is what you are carrying into the dark tonight. That is the answer to the question the title asked. You have never seen the center of the galaxy as it actually is. No human has invisible light, and no human has seen it in the present tense, and no human ever will in this lifetime or the next many thousands of lifetimes. But what you have seen through infrared and radio, through mathematics and patience and the slow accumulated craft of 2 groups of astronomers watching one small star go around and around an invisible point, is something true, 26,000 years old and true. A message from the deep past, from the heart of the thing you are orbiting, sent before your ancestors had words and received by you, tonight in the dark. That is a good thing to take into sleep. Wherever you are listening from tonight, whether the lamp beside you is still on, whether the rain is on the windows, whether it is very late or very early or somewhere gently in between, I hope this slow wander through the center of things has left you with something. A little of the strangeness, a little of the wonder at the precision of what has been learned, a little of the comfortable vertigo of knowing that you and the earth and the sun and everything you have ever known or loved is slowly, gracefully, at 220 kilometers per second, going around something enormous and dark and ancient at the heart of a galaxy in which there is still quite a lot left to find out. If you enjoyed tonight's quiet journey through the galactic center, a gentle like or subscribe would mean a great deal to this sleepy little channel. Small creators like me really do rely on your support to keep these going, and I would love to know where you are listening from tonight and what time it is in your corner of the world. That question for me never gets old. Until next time, close the books, dim the lamp, class is over, sleepy scholar.